So last time we had finished the proof. It was a long proof that polynomial hierarchy randomly reduces to parity P. So this we had achieved by replacing both there exist and for all quantifiers, all of them by a single parity quantifier, right? And hence we have shown that polynomial hierarchy can be randomly I mean, if you can solve sharp P or sharp parity set, then you can solve any problem in pH in randomized polynomial time. But our original goal, remember, was to show deterministic containment, right? Toda theorem says that pH is actually contained in P raised to sharp set. So if you can solve sharp set, then you can solve pH in deterministic polynomial time. So how do we show that? This is the question of de-randomization. So we'll de-randomize this random reduction by first amplifying this parity difference of 0, 1 to higher moduli. So we'll go from mod 2 to mod 2 raised to m. Okay, so that as we sum up over all possible random choices, the formula value mod 2 raised to m appears large or small in magnitude. So that will eliminate the need for randomly chosen string R. So lemma 2 is the lifting lemma. Say you have a Boolean formula psi, then you can lift the values of hash psi. So 1 mod 2 will lift to minus 1 mod 2 raised to m plus 1, and 0 mod 2 will lift to 0 mod 2 raised to m plus 1. So this we will do by using these operators, addition and multiplication. So f plus g, as seen before, is it uses a new variable u. So on u0 it takes value f, and on u1 it takes value g. Okay, and multiplication will be the multiplication. So this is copy of variable x, which we call y. So it takes and of f of x and g of y. You can see why this plus and multiplication. What is the effect of plus and multiplication? It is just the number of satisfying assignments gets added, respectively gets multiplied. So let us initialize, it will be an iterative process. So let us initialize phi 0 to be psi. So this is correct up to value mod 2. And now let's define the next step, which is a very clever formula. So it is phi I plus 1. This will be the previous formula. You cube it, then you add it 4 times. So that's depicted by 4 multiplication. You multiply it 4 times, add 3 times, and then add the 2 things. Okay, so this is the addition multiplication happening on the previous phi I. So let's say phi 0, and this will give you phi 1. Okay, so it's a new formula, it will have more variables, and the claim for this is that the number of satisfying assignments, if we keep building phi I like this, the number of satisfying assignments for phi I is minus 1, okay, let me write it a bit more clearly. So if you start with number of satisfying assignments of phi I to be minus 1 mod 2 raised to 2 raised to I. Then the number of satisfying assignments of phi I plus 1 is also minus 1 mod a much higher modulus. Okay, so from 2 raised to I in the exponent, you are moving to square of that, 2 raised to I plus 1. The modulus basically gets squared, okay, and the exponent gets doubled. So this is doubling the exponent, squaring the modulus. And similarly, if the number of satisfying assignments to begin with is 0, then it remains 0 in the higher modulus. Okay, so that is the interesting property of this 4 times cube plus 3 times 4th power. So if you haven't seen this formula before, then you may be surprised how this is happening, and that is a simple calculation. So let's see the proof. Simple modular arithmetic. So this formula is an inspired formula. You cannot come up with this formula directly. It's actually reverse engineered. But once I give you the formula and the claim, then it's easy to prove, which is as follows. So observe that four times minus 1 plus 2 raised to j q cube. Okay, so if we have a number which is minus 1 mod 2 raised to j, we cube it, multiply it by 4 and then add 3 times the same number, 4th power. Okay, then what happens? What happens is we'll actually get its value minus 1 in the higher modulus, which is 2 raised to j plus 1. How? So let's write it, let's check it. So this is 4 times minus 1 plus use the expansion of cube. So you get 3 times 2 raised to j q, and then you will get multiples of 2 raised to j plus 1. So we can drop those, and the second one gives you 1 because it's even power, 4th power, minus 4 times 2 raised to j q, right, which is what? So this is minus 4 plus 3, so it's minus 1, and you can see that you'll get 4 3s are 12, right? So 12 minus 12, so it will cancel, and you will get in the higher modulus 2 raised to j plus 1. No, much more than that, 2 raised to 2j. Okay, because next when you look at the expansion in cube, the third term is actually 2 raised to j square, and in 4th power also the third term is 2 raised to j square. So actually those are the terms, those are the only terms we have dropped. They are multiples of 2 raised to 2j or 2 raised to j whole square, right? And modulo this, the value is still minus 1. So that essentially gives you the proof of the first case. So if you start with minus 1 mod 2 raised to j, then you end up with minus 1 mod 2 raised to 2j. There is a squaring, right? So modulus, so just remember that modulus gets squared. That proves the first case. Let's go to the second case. So in the second case, what do you get? You have 4 times. Now we are talking about 0 mod 2 raised to j, right? So you have just 0 plus 2 raised to j q plus 3 times 0 plus 2 raised to j q fourth power. And what is this? So this is 0 mod again 2 raised to 2j. In fact, here you are getting more. You are getting 2 raised to more than 3j actually, but we will not need that. We will be happy with just 0 mod 2 raised to 2j. And from this we learn, thus in both cases mod 2 raised to j lifts to mod 2 raised to 2j. And that is what the claim said, that 2 raised to I will become 2 raised to I plus 1. Okay, so this magical formula, this recurrence for phi I plus 1, this lifts the values mod 2 to mod 4, so mod 2 to mod 2 square to mod 2 raised to 4. It grows very fast. So this also means that by induction on I, right, this phi I plus 1 formula, if you keep repeating it, so by induction on I, deduce that phi I for I equal to around log m, go up to log m, and you will get what you wanted in lemma 2. You wanted 2 raised to m plus 1, right? So let me just fix it properly. So just use log 2m ceiling. Okay, so this will be more than 2 raised to I will be, in fact, even if you take this, so 2 raised to I will be more than or 2 raised to 2 raised to I. 2 raised to 2 raised to I will be more than 2 raised to m plus 1. Okay, so for already, I mean, very fast, very rapidly, phi I will approach the modulus, correct value, modulus 2 raised to m plus 1. For this I, phi I will have the properties claimed in lemma 2. Okay, so lemma 2 is proved this way. And note that number of variables in phi I have grown. So as you go forward using the recurrence for phi I plus 1, the variables also blow up, right? So the formula size is blowing up, but by how much? So this has grown only by a log m factor. Okay, so why is that? See, when you multiply, then you are growing the you are actually doubling the variables. And when you add f plus g, then you are introducing one new variable. In every step, we are actually cubing or taking fourth power and then adding, taking a sum, right? So I should say it is something like doubling each time. So it will go up to 2 raised to I. So let me correct this. Only by a factor of 4 raised to I, which is like what? Which is something like m square. Okay, so lemma 2 only wanted a polynomial time transformation, and this is polynomial time. In terms of m, it is only quadratic. So this is how the formula will blow up, but not by too much. And the value hash phi will become correct mod 2 raised to m plus 1. That's the trade-off. So this finishes the proof of lemma 2. Okay, so proof of lemma 2 is done. And let us now come back to our question before lemma 2, which was how do we de-randomize the pH reduction to parity P. So let's now move to, let's now de-randomize the reduction of pH to parity P. Okay, how is that done? So this is the proof of, this finishes the proof of Toda's theorem. So take a problem in pH. Let x be the input string. So by lemmas 1 and 2, what you get is we have a polytime Turing machine in fact NDTM, because it's to do with counting the number of paths. So basically parity sat, reduction to parity sat, right? So we have a polytime NDTM, M, and this blow up exponent, the size of the certificates. So M is the polynomial blow up of the certificate length, such that if X is a yes string for the problem L, then the probability in fact M was the length of the random bits, the random string length. So probability over the random string that the accepting path of M XR, this NDTM has how many accepting paths? Let's say -1. Okay, so if X, so remember how this proceeds using lemma 1, 2. So yes string will be converted into a, there is an NDTM such that for yes strings on random choice of R, the number of accepting paths was odd, and then it was boosted up to -1 mod 2 raised to m plus 1 with high probability. This is true for most of the random strings greater than or equal to 2/3. On the other hand, if x is a no string, then the probability over these r's is less than 1/3. Okay, so depending on yes and no, the probability, the number of r's will drastically change. So for the yes strings, it's 2/3 r's. For the no string, it's 1/3, at most 1/3 r's, such that this number of accepting paths of mx comma r NDTM is -1 mod high modulus. Moreover, it's also true that for all x and for all r, the number of accepting paths of mx comma r, this is either 0 or 1. Sorry, 0 or -1. Okay, so it takes only two values, no matter yes no string and which random string you choose. This is again because to begin with, the parity is only 0 or 1, the only two options 0 1 mod 2, and this 0 1 mod 2 will get lifted to only two values 0 -1 respectively, right. So there are only two possibilities, mod 2 raised to m plus 1, and they happen with the correct probability. This is what we have learned till now. Okay. Now let us modify the NDTM. So now the idea is replace random bits by non-deterministic ones. Okay, so de-randomization idea here is replace the random bits by non-deterministic bits. So we will actually not, the algorithm will not use R as a through random coin tosses, but it will just try to guess R, and so it will remain NDTM. And now let us count the number of satisfying assignments. So define NDTM m prime that on input x guesses R and accepts if and only if m accepts x comma r. Okay, so now m prime will not choose R, but it will just guess R. It remains an NDTM though. And so how many accepting parts does m prime have? So number of accepting paths of m prime x equals, go over all R, and then number of accepting paths for this R. Of M x comma R. Right. So now on this we have some control, right? This number of accepting paths of mx comma r, as we have observed before, this is either 0 or -1 mod 2 raised to m plus 1. So let's do that. So its value mod 2 raised to m plus 1 is, it is see, if x is a yes string, then for 2/3 hours this is -1. So it is between 2/3 of 2 raised to m. So at least these many times you get -1, and then maybe you get few more -1s. Otherwise, you get 0, right? -1s and 0. So it is between this value and -2 raised to m. Okay, so it's on the negative side, but very negative, right? So if you look at the magnitude, it's close to 2 raised to m. This is if x is a yes string. Otherwise, no more than 1/3 of r's can give you -1. So 1/3 of 2 raised to m give you -1. The remaining give 0. So that's 0. If x is not in L. Okay, so basically think of this case, x no string case, as either all the r's will give you 0. That's a good case. But in the worst case, what can happen is there is only 1/3 of 2 raised to m many -1s. Okay, so this we can think of this as being closer to 0, and the magnitude is small. Okay, magnitude. So now we have a gap in the magnitudes. So this means that the magnitude is either close to either 2 raised to m or 0. Okay, it's either close to 2 raised to m or 0. If you look at the positive value, you can divide it. Basically, you are dividing it 2 raised to m, 0 to 2 raised to m interval in 3 parts. Either you are toward the part closer to 2 raised to m or towards the part closer to 0 with a good gap. Okay, gap is defined as given above. So which means that computing the number of accepting paths of m prime x solves L. Right, and solves L where? In P to the sharp P. and L was any problem in pH, right? So you have shown that pH is contained in P to the sharp P. So that finishes Toda's theorem. Okay, so finally, after several classes and a long proof, we have finished the proof of Toda's theorem. Right, so remember the key steps were: first you replace two quantifiers by single quantifier, which is parity. So you reduce pH to randomly reduce pH to parity sat, and then you de-randomize that by jacking up the moduli. So the proof used and then invented a new class parity P, okay, which doesn't appear in the final statement. Which was not asked in the statement. Okay, so this is why it's a very interesting proof. It's a very, although it's a long proof, but it actually invents complexity classes and methods. You used hash function, for example, and randomization itself is something new here in the proof. So randomization here was a simplifying tool. Simplifying tool or notion in this proof. And now we will see, we'll actually use randomization. We now use randomization to compute. And not just analyze. Okay, so now we will define something called probabilistic Turing machines.